right. Back to the logic. I feel like I lost a little momentum, but I had a really nice thing to do. So, but I do want to just get through this now so that I can enjoy the game and talk with my family about it. So I don't think it's going to take too much longer, really. But let me just get set up again in case this will be useful to anybody. Yeah. Give me 1 second. All right. Purse. What were you talking about, Purse? So the same warnings that have been given against imagining that induction rests upon the uniformity of nature might be repeated in regard to hypothesis. I remember actually learning this in school. In college even. Where they're like, induction works because if something happens regularly enough, you assume that, like, nature is uniform, and therefore, things that are similar, it happens the same way. That's what does it. He's like, no, that's not what you have to assume. Here is there, such a theory not only utterly fails to account for the validity of the inference, but it also gives rise to methods of conducting in it which are absolutely vicious. And here, vicious has a particular sense in logic, like a vicious circle, but he might mean it. It's just like, he might really just hate it. I don't know. There are no doubt certain uniformities in nature, the knowledge of which will fortify a hypothesis very much. For example, they suppose that iron, titanium, and other metals exist in the sun, because we find in the solar spectrum many lines coincident in position with those which these metals would produce. And this goes back to spectroscopy, which was using a certain kind of instrument to break up the radiation from the sun in order to discover what kinds of metals were in it. And being like, well, ultimately that observation is hypothetical. And this hypothesis is greatly strengthened by our knowledge of the remarkable distinctiveness of that particular line of characters observed. I've never looked through a spectroscope myself, so I can't attest to that. But like, if it looks really, really different when you look at certain metals versus other things, what kinds of light it gives off or radiation it gives off through the spectroscope, like when you look at the sun, you see the same thing. You're like, well, that's pretty distinctive. That probably means that that's there. But until much later, when there were other methods of doing it, like you were never going to go to the sun and see it for yourself. So Auguste Comte, who was this guy who was a positivist, he was like, that's one thing we'll never know, what's inside of the sun. And it's like, well, actually you can. You just need to use pretty good hypothetical reasoning in order to infer it with this instrument. But such a fortification of a hypothesis is of a deductive kind. And hypothesis may still be probable even when such reinforcement is wanting. There's no greater nor more frequent mistake in practical logic than to suppose that things which resemble one another strongly in some respects are any more likely for that to be alike in others. That this is absolutely false admits of rigid demonstration. You don't even have to do the rigid demonstration, but he's like, but in so much as the reasoning is somewhat severe and complicated, requiring use of letters, the reader would probably find it distasteful, and I admit it. But more recently, and in a slightly different way, you can find all of these funny graphs that people put together about the correlation between ice cream sales and divorce rates in Minnesota and things like this, which kind of show how ridiculous it is. This kind of thinking is in a certain respect, but he's thinking of just like basic similarities. And after his example, I'll give a more modern example that might fit with what he's talking about. The comparative mythologists occupy themselves with finding points of resemblance between solar phenomena, things that happen with the sun, like an eclipse, rising and setting. I don't know what they are. And the careers of the heroes of all sorts of traditional stories. And upon the basis of such resemblance, they infer that these heroes are impersonations of the sun. They're like, look, this is where they must have been getting it from. All of these stories are about the sun because it looks like the sun, So too does the hero have his eclipse or whatever. If there be anything more in their reasoning, it has never been made clear to me. An ingenious logician, intending to show how futile all that is, wrote a little book in which he pretended to prove in the same manner that Napoleon Bonaparte is only an impersonation of the sun. It was really wonderful to see how many points of resemblance he made out. Of course, Peirce doesn't give us any, so he's just like, go find this book that I don't name if you're interested. But the truth is, any two things resemble one another just as strongly as any two others. if recondite resemblances are admitted. This is, I think, a really powerful insight, that resemblance is a relationship one can always discover. One can always discover resemblances. Everything that's analogous is also disanalogous, depending on how many resemblances. So when people kind of start going around and discovering kind of messages or signs in the world, I don't find anything particularly wrong with that as a kind of moral way. But of course, they're discovering resemblances and not looking at all of the dissimilarities. They're not paying attention to those ones. Maybe more similar to the kind of sun, every hero is a sun god hypothesis, is the things that used to be on like the History Channel. These kinds of documentaries where they'd be like, all of the great religions are the same or whatever. And they would kind of just show relationships between stories that people tell and be like, well, those resemblances prove identity. It's like, no, there are lots of things that might be similar between them, but look at all the things that are different. And that's, of course, what the documentary really leaves out. It leaves out all of the differences. It only focuses on the similarities, and then you're like, oh, yes, therefore it's all one big story or something like that. So, but in order that the process of making a hypothesis should lead to a probable result, the following rules must be followed. The hypothesis should be distinctly put as a question before making the observation which are to test its truth, which also would be a reason not to put it in a syllogistic form, because you can't really put a question in a syllogism. In other words, we try to see what the result of predictions from the hypothesis will be. Number 2, the respect in which regard to the resemblances are noted must be taken at random. We must not take a particular kind of predictions for which the hypothesis is known to be good. Number 3, the failures as well as the successes of the predictions must be honestly noted. The whole proceeding must be fair and unbiased. So when you see things that are dissimilar, that would be relevant at least to your hypothesis about it, you should make that sense of that too. Okay. Some persons fancy that bias and counter-bias are favorable to the extraction of truth, that hot and partisan debate is the way to investigate. This is the theory of our atrocious legal procedure. In the United States, that is, because he was American. And there is an adversarial legal system. Not every legal system is like this. I'm not sure that necessarily there's any legal system that has something that he would approve of, probably, but I'm pretty sure the Italian legal system is one that's kind of like based around truth discovery or something. It has like a different kind of procedure that's involved in it that is explicitly non-adversarial. I don't know if that's true, but I remember hearing that once. But I don't think that means that the Italian legal system is great or something, just because its self-conscious methodology is supposed to be better. But logic puts its heel upon this suggestion. It irrefragably demonstrates that knowledge can only be furthered by the real desire for it, and that the methods of obstinacy, of authority, and every mode of trying to reach a foregone conclusion are absolutely of no value. Now, I kind of both agree and disagree with Peirce, because one of Peirce's more famous papers is called The Fixation of Belief, and there he kind of talks about these various methods of obstinacy, of authority, and also, or is that How to Make Our Ideas Clear? I think I kind of confused those two papers that he wrote together. Those are two way more famous papers than this one. And the idea that they have no value, in fact, when you read that essay, he shows that they do have kind of limited value, even though he's pretty dismissive of it in some ways for what he hopes will kind of replace it. Appealing to authority is not the end point of human inquiry. But the end point of human inquiry for Peirce is truth, but only because truth is kind of infinitely at the end of inquiry. It's not a point that you arrive at. We kind of asymptotically approach it. So on the one hand, I agree that like hot and partisan debate is a really, really bad method for discovering the truth of things. One reason might be that neither side represents the truth. So like a decision between them would be arbitrary if we were thinking about what the truth would be. Both sides could be wrong. Even if we thought that we had split up the possibility of a discourse into a yes or a no on a proposition, the reasons given for that also might be false, something like that. So that's one reason why it wouldn't work out logically. But one reason why I kind of disagree is that doesn't mean that it's of no value, because there are values other than truth values. But anyway, and he kind of suggests that again in other pieces. But here he's just making, I think, the simple point that debating things doesn't necessarily get you closer to the truth of them. These things are proved. So he's like, there's nothing worse than authority, but let me just claim that these things are proved. And then he says, the reader is at liberty to think so or not, as long as the proof is not set forth, or as long as he refrains from examining it. It's like, well, okay, we'll give it to us. But he's like, but it would tire you out. So okay, so he is asking you to accept it on authority. Is that irony? I don't know. Just so he can preserve, if he likes, his freedom of opinion in regard to the propositions of geometry. Only in that case, if he takes a fancy to read Euclid, he will do well to skip whatever he finds with A, B, and C, etc. For if he reads attentively that disagreeable matter, the freedom of his opinion about geometry may be unhappily be lost forever. So here he's having a bit of fun. He's kind of taking the piss, as British people would say. He's taking the piss when people are like, well, I want to be free to think also, whatever I think. He's like, well, there are some matters on which having the freedom of your opinion is just being ignorant. Like a matter like whether their primes are infinite or not, which is proved by Euclid. It would be silly to think that you have freedom of opinion on that. Like there is a proof for it, and so he's saying that the same thing is true of the legal procedure. It's like legal procedure is not about truth. It has nothing to do with truth. It's ridiculous, and you can prove it. It's like, but don't bother yourself if you want to still think about that, I guess. How many people are there who are incapable of putting to their own consciences this question? Do I want to know how the fact stands or not? And he's getting kind of like aggressive in this section, a little cranky. The rules which have thus far been laid down for induction and hypothesis are such as are absolutely essential. There are many other maxims expressing particular contrivances for making synthetic inferences strong, which are extremely valuable and should not be neglected. Such are, for example, our Mr. Mill's four methods. So this refers to John Stuart Mill's work from the 1840s called A System of Logic, and in some sense, sets forth a kind of different look at what especially inductive reasoning is. And there are these various kinds of heuristics or maxims, you could call them, for how to go about thinking about induction for science, for scientific experiments, or for the time anyway. And he's like, those can be useful. That's great. Nothing wrong with them. Nevertheless, though, in the total neglect of these, inductions and hypotheses may, and sometimes do, attain the greatest force. So they're not necessary for what you need. He's like, what's necessary is the stuff that I've talked about, which is, what's the nature of these inferences? Section 4. Classifications in all cases perfectly satisfactory hardly exist, even in regard to the great distinction between explicative and ampliative inferences. So here the F got lost, as I thought. So explicative and ampliative inferences, which is very similar to the distinction between synthetic and analytic inferences that he was talking about before. So again, he keeps changing the nature of his terms. I don't know if there would be a reason to say this rather than those, but there probably is, and I'm just ignorant of it. I don't know what it would be. Examples could be found which seem to lie upon the border between these two classes, and to partake in some respects of the characters of either. And this is what, again, Quine puts forward a bunch of these border cases in his famous paper, which was written long after this, called Two Dogmas of Empiricism. And one of the examples he talks about, which doesn't seem like a border case when you start out, is like the meaning of bachelor, because this is always used like a bachelor is single. That's an analytic inference. And he's like, well, how do you actually know that? They're like, people say like you have to know the meaning of the word, but like the meaning of the word is something you've got to go figure out. So anyway, he makes these kind of weird arguments that I found to be persuasive when I remembered them. I don't remember them very well now. But for him, he's like, really nothing is, ultimately, there is no such thing as a perfectly analytic inference. Everything is synthetic. Everything requires you to be out in the world and just learning stuff. The same thing is true of the distinction between induction and hypothesis. In the main, it is broad and decided. By induction, we conclude that facts, similar to observed facts, are true in cases not examined. So we go back to the beans, like, I look at the beans. I took the beans out of the bag. I look at them. They're all white, so the beans in the bag are white. I didn't look at all the beans in the bag. Okay, but by hypothesis, that's like the beans are already here. I'm looking at the beans in the bag. Those probably came from the bag. Different. By hypothesis, we conclude the existence of a fact quite different from anything observed, from which, according to known laws, something observed would necessarily result. The former is reasoning from particulars to the general law, the latter from effect to cause. The former classifies, the latter explains. It is only in some special cases that there can be more than a momentary doubt to which category a given inference belongs. One exception is where we observe not facts similar under similar circumstances, but facts different under different circumstances. The difference of the former having, however, a definite relation to the difference of the latter. Such inferences, which are really inductions, sometimes present, nevertheless, some indisputable resemblances to hypotheses. That's hard to parse because, like, coming up with an example that would fit that, differences between things that are also under different circumstances. It's like, I don't know. That seems like it could be almost anything. So he's going to give us some examples here, but they find them a bit puzzling, not just because they're old-timey. I'll do my best to explain them, but because Peirce is a weird guy. What he thinks makes something clear is not always what anyone else would think makes something clear, but it might be worth, nevertheless, struggling through this passage. That's not a great vote of confidence. I'm like, I love this piece. I'm like, it's very difficult and it's unclear. Knowing that water expands by heat, we make a number of observations of the volume of a constant mass of water at different temperatures. Water expands by heat, so we know that, right? That's the rule. We make a number of observations of the volume at different temperatures. So we're kind of like, doing little tests. Okay, well, what's the relationship between the temperature and the expansion? The scrutiny of a few of these suggests a form of algebraical formula, which will approximately express the relation of the volume to the temperature. It may be, for instance, that the volume, V being the volume, relative volume, and T the temperature, the few observations examined indicate a relation of the form. Volume equals 1 plus some constant T plus some constant T squared plus some constant T cubed. Now, he doesn't really explain why it would possibly be like this, but let me just say that what you might remember about volume is that volume can be cubic in its nature, right? It's a kind of cubic thing. So he's just kind of taking, he's like it's some volume at all of these various these various constants, including when T is squared and T is there's going to be some kind of relationship there. So this is just kind of a guess. And then it gets confirmed by all these observations. Upon examining observations at other temperatures taken at random, the idea is confirmed, and we draw the inductive conclusion that all observations within the limits of temperature from which we have drawn our observations could equally be so satisfied. So we do all these little kind of experiments about the temperature in relationship to the volume. We're like, it worked in this cases. And then we say, actually that's probably going to be true anytime we take the temperature and we relate it to the volume. There we go. Bingo. Having once ascertained that such a formula is possible, it is a mere affair of arithmetic to find the values of A, B, and C, which will make the formula satisfy the observations best. That is what physicists call an empirical formula, because it rests upon mere induction and is not explained by any hypothesis. We just know that it works. We don't know why it works. We just know that it does. It's an empirical formula. And it's useful, because then I can take other measurements more quickly, and I know how to relate them to each other. Great. Such formulae, though very useful as a means of describing in general terms the results of observations, do not take any high rank among scientific discoveries. The induction which they embody, that expansion by heat, or whatever other phenomenon is referred to, takes place in a perfectly gradual manner without sudden leaps or innumerable fluctuations. Although really important, attracts no attention because it is what we would naturally anticipate. We would guess that temperature would gradually rise if we were to heat something, for instance. Same thing for the expansion of the volume of water. But the defects of such expressions are very serious. In the first place, as long as the observations are subject to error, as all observations are, the formula cannot be expected to satisfy the observations exactly. Because if the way we got the formula was based on testing stuff, those observations are, and measuring stuff, those observations are always subject at least to the error, not of just the human person, but of the instrument itself. But the discrepancies cannot be due solely to the errors of observations, but must be partly owing to the error of the formula, which has been deduced from erroneous observations. Moreover, we have no right to suppose that the real facts, if they could be had free from error, could be expressed by such a formula at all. They might perhaps be expressed by a similar formula with an infinite number of terms. Like they're like, the truth is this kind of formula that goes on forever, which wouldn't be usable but would be truer. But of what use would that be to us, since it would require an infinite number of coefficients to be written down? When one quantity varies with another, if the correct corresponding values are exactly known, it is a mere matter of mathematical ingenuity to find some way of expressing the relation in a simple matter. And this is something that, sometimes physicists will take beef with engineers who are like, maybe more likely to use empirical formulas that kind of work, things that are known to work, even though, they might not be exactly true. The physicists might be more interested. Depends on the kind of physicist, but sometimes they beef about this kind of stuff. If one quantity is of one kind, say a specific gravity, and the other of another kind, say a temperature, we do not desire to find an expression for the relation which is wholly free from numerical constants, since if it were free from them when, say, specific gravity is compared with water, and temperature is expressed by the centigrade thermometer were in question, numbers would have to be introduced when the scales of measurement were changed. We may, however, and do desire to find formulas expressing the relations of physical phenomena which shall contain no more arbitrary numbers than changes in the scales of measurement might require. We don't want to add in a bunch of arbitrary terms in our formulas of stuff, about how stuff is related. We want it to be kind of concise and clean and efficient, which is a different kind of desire than maybe like what would be true. What guarantees the truth will be clean and efficient and nice and neat? It's what we want from it. That's not necessarily what is the case. There's no reason to suppose that would be the case. When a formula of this kind is discovered, it is no longer called an empirical formula, but a law of nature, and is sooner or later made the basis of an hypothesis, which is to explain it. These simple formulae are not usually, if ever, exactly true. What? So this is one of the weird things that Peirce kind of casually slips in here, which is like, the laws of nature are not true. Exactly. They're useful. And the great triumph of the hypothesis comes when it explains not only the formula, but also the deviations from the formula. So it's like the hypothesis shows us why this formula works most of the time, and it also shows us why sometimes we get readings that don't conform to it, because like there's some other thing that's not fully accounted for. There's some other kind of weird little example where it helps us see things further. It helps us see further into the phenomena that we're trying to describe. In the current language of the physicists, a hypothesis of this importance is called a theory, while the term hypothesis is restricted to suggestions which have little evidence in their favor. There is some justice in the contempt which clings to the word hypothesis. That's merely a hypothesis. To think, or as my students will sometimes say, "Oh, you're just pulling that out of your ass." It's like, well, sometimes your ass is a good place to go for something, but no, it's really not. It's like some hypotheses are better than others. Because if hypotheses are arguments or inferences, it doesn't mean that they're all equal. They have a similar form. They're making a similar kind of inference. They belong to the same class, but they're not all of the same strength or value. It depends on all sorts of things, but you could say one thing it depends upon is like if we're using a rule to try to infer what the case is from the thing that we're observing. We're observing something, trying to say, okay, let's think of a rule that would then explain the case. Well, one thing we would think about is that rule one that we would accept already in other ways? Or is it something that we've kind of like ad hoc made for the purpose of this particular observation? Okay. Another thing you might think about is, does it really fit? Does it explain more or less than a different rule would? Are there better ones? There's lots of different things that we might use to evaluate the strength of a hypothetical inference or argument. To think that we can strike out of our own minds a true preconception of how nature acts is a vain fancy. As Lord Bacon well says, I also like this quote. This is kind of quoted a lot. That's Francis Bacon as Lord Bacon. The subtlety of nature far exceeds the subtlety of sense and intellect, so that these fine meditations and speculations and reasonings of men are a sort of insanity, only there is no one at hand to remark it. The successful theories are not pure guesses, but are guided by reasons. Now, what's funny is that this quote is often used to say almost exactly the opposite of what I think Peirce is saying, which is that, like, no, sometimes it's used to say something like, well, science is exact, whereas what people think when they're kind of just, speculating, it isn't the case. But, I mean, that might be one aspect of what I think this quote means or how you might apply it, but I think what he's trying to say here is that There's no reason to believe that nature conforms to the laws that we give to it exactly. The laws we give to it allow us to understand certain things about it that are not well understood otherwise. And something that Peirce will say in other places is that, why do we call them the laws of nature rather than the habits of nature? And some kind of contemporary scientists, namely Lee Smolin, who's a physicist, has kind of championed this way of looking at the so-called laws of nature. The kinetical theory of gases is a good example of this. This theory is intended to explain certain simple formulae, the chief of which is called the law of Boyle, or Boyle's law. That's how I learned it. It is that if air or any other gas be placed in a cylinder with a piston, and if its volume be measured under the pressure of the atmosphere, say 15 pounds on the square inch, and if then another 15 pounds per square inch be placed on the piston, so we could push air down in a little gas, in a little cylinder, we're compressing the air basically. And if another 15 pounds, the gas will be compressed to 1/2 its bulk. And in similar inverse ratio for other pressures. So there's a relationship between pressure and volume. The hypothesis which has been adopted to account for this law is that the molecules of a gas are small, solid particles at great distances from each other, relatively to their dimensions, and moving with great velocity without sensible attractions or repulsions until they happen to approach one another very closely. So they're not like magnetized in a way that would deeply affect their trajectories. They're not in a kind of magnetic field. Only when they get really close do we start to see those kinds of effects of attraction or repulsion. So they're like these little billiard balls. That's the way it was. I learned it too. And this still might not be the most accurate way to understand it, but it's a useful hypothesis. Admit this, and it follows that when a gas is under pressure, what prevents it from collapsing is not the incompressibility of the separate molecules, which are under no pressure at all, since they do not touch, but the pounding of the molecules against the piston. The more the piston falls and the more the gas is compressed, the nearer together the molecules will be. The greater number there will be at any moment within a given distance of the piston, the shorter the distance which any one will go before its course is changed by the influence of another. So one thing maybe you learned this in school, but like when you're trying to like push down, I'm looking at a French press. It's not the best example because it's full of holes, but any kind of time when you're trying to compress air, like it gets harder and harder. You need more and more pressure to kind of compress the air further when you're kind of like, what's a place where you're trying to compress air? I don't know. Think of one. And it's almost, I think we all learn it so early on in the school that like we can think of gas as a bunch of molecules and particles that it's hard for us to even imagine that that's a thing that people had to infer. But that was actually like a major inference. It wasn't, and as he's going to talk about. This explains Boyle's law. The law is not exact, but the hypothesis does not lead us to it exactly. For in the first place, if the molecules are large, they will strike each other oftener when their mean distances are diminished, and will consequently strike the piston oftener, and will produce more pressure upon it. On the other hand, if the molecules have an attraction for one another, they will remain for a sensible time within one another's influence. So he's basically showing you could come up with other hypotheses why you would think that it made the particles larger when you added pressure to it. It seems weird. Like it doesn't seem any reason to accept that hypothesis, but that could be another hypothesis that you adopted that would also explain it. When the kinetical theory of gases, that just means moving, that gases are kind of moving around, was first proposed by Daniel Bernoulli in 1738, it rested only on the law of Boyle and was therefore pure hypothesis. It was accordingly quite naturally and deservedly neglected. But at present the theory presents quite another aspect, for not to speak of the considerable number of observed facts of different kinds with which it has been brought into relation, it is supported by the mechanical theory of heat. Mechanical theory of heat meaning that heat is also made up of moving particles moving very quickly. That bringing together bodies which attract one another, or separating bodies which repel one another, when sensible motion is not produced nor destroyed, is always accompanied by the evolution of heat, is little more than an induction. Because you just see it, like when you kind of rub your hands together, your hands get hot. That kind of thing. But as we start to kind of bring these various inferences together, we're making this hypothesis about the kinetic theory of gas much more persuasive, much stronger. Now, it has been shown by an experiment that when a gas is allowed to expand without doing work, a very small amount of heat disappears. This proves that the particles of the gas attract one another slightly, and but very slightly. It follows that when a gas is under pressure, what prevents it from collapsing is not any repulsion between the particles, since there is none. So it's ruling out this other hypothesis that there's a kind of like almost, I mean, he's not saying magnetic because it would have been a different force that doesn't exist, but some kind of force of the attraction between the gas particles themselves, like they were kind of some special material or something. No, that's not what's happening. Now, there are only two modes of force known to us. This is no longer true, by the way, but, sometimes things change in science. That's kind of what he's talking about. Now, there are only two modes of force known to us, force of position or attractions and repulsions. That's one name of it. The force of position, that's like attraction and repulsion. So how we would very simply and basically understand things like electromagnetism. Actually, even saying that shows that, it's not like that anymore, but whatever. And force of motion. Since, therefore, it is not the force of position which gives a gas its expansive force, it must be the force of motion. So see, like all these things, he's like, you don't just go from the fact that like gas gets harder pressurized. You don't necessarily go to a theory that it's kinetic. There could be all these other hypotheses that you have. And by slowly ruling those out, you're making the other hypothesis stronger because we only know of these other two forces. So if it's not this one, it's got to be this one, right? It is to be observed, except, there might be more forces in the world. It is to be observed, however, that it supposes the same law of mechanics, that there are only two modes of force, which holds in regard to bodies such as we can see and examine, to hold also for what are very different, the molecules of bodies. So two objects kind of colliding with each other, they're like, we're applying that same idea to have very, very tiny things that are molecules. And Peirce is kind of pointing to something that would later be discovered, which is at very small scales, different laws or rules apply. So, the discoveries of quantum mechanics. Such a supposition has but a slender support from induction. Our belief in it is greatly strengthened by its connection with the law of Boyle, and it is therefore to be considered a hypothetical inference. Yet it must be admitted that this kinetical theory of gases would deserve little credence if it had not been connected with the principles of mechanics. The great difference between induction and hypothesis is that the former infers the existence of phenomena such as we have observed in cases which are similar, while hypothesis supposes something of a different kind from what we have directly observed, and frequently something which it would be impossible for us to observe directly. That's one of the things that's really important about hypothesis. You can't always make direct empirical observations of things that are, like, let's say, super, super tiny. Sometimes technology gets better, and it allows you to see things. We have electron microscopes now. We can see more stuff. See more stuff. See it. Sort of. It's, something more complicated than seeing is going on with even early microscopes. But, okay, we use the kind of metaphor of seeing through a microscope. You can read Ian Hacking's great piece, which I think is called How to See Through a Microscope or something like that, which talks about this. But accordingly, when we stretch an induction quite beyond the limits of our observation, the inference partakes of the nature of hypothesis. It would be absurd to say that we have no inductive warrant for a generalization extending a little beyond the limits of experience, and there is no line to be drawn beyond which we cannot push our inference. Only it becomes weaker the further it is pushed. And we all kind of know this the more you kind of put conditions and reasons on a kind of guess about something, the less believable, the less credence that it bears. It becomes kind of convoluted. Yet if an induction be pushed very far, we cannot give it much credence unless we find that such an extension explains some fact which we can and do observe. Here then we have another kind of mixture of induction and hypothesis supporting one another, and of this kind are most of the theories of physics. So you can't really push an induction very far, but it's a stronger kind of argument. You can go really, really far with a hypothesis. It just gets weaker and weaker, like a radio signal way out in space. 5. That synthetic inferences may be divided into induction and hypothesis in the matter here proposed admits of no question. The utility and value of this distinction are to be tested by their applications. It's like, so we can make this distinction? Should we, though? Well, it depends on whether it matters. Induction is plainly a much stronger kind of inference than hypothesis, and this is the first reason for distinguishing between them. Hypotheses are sometimes regarded as provisional resorts, which in the progress of science are to be replaced by inductions. But this is a false view of the subject. Hypothetic reasoning infers very frequently a fact not capable of direct observation. It is an hypothesis that Napoleon Bonaparte once existed. How is it that hypothesis ever to be replaced by an induction? It may be said that from the premise that such facts as we have observed are as they would be if Napoleon existed, we infer by induction that all facts that are hereafter to be observed will be of the same character. We can't do a bunch of experiments to discover whether Napoleon existed because, they were trying to infer the case. We're trying to infer a particular case. And this might be one way to think about the difference between what are broadly called, the natural sciences and things like the social sciences and the humanities. Now, the social sciences, hard to say because sometimes they want to really resemble the natural sciences. But often what we're trying to think about or explain, or maybe not even explain, just kind of interpret, in something like the humanities, is a case. Like, what is the case? And that's not something that's always susceptible to, well, it's certainly not susceptible to deductive reasoning in any interesting way, most of the time. Though we can, again, as he said, we can always kind of make it look like it is deductive. That would be silly, though. But it's also not really always capable of inductive reasoning because you can't, let's say, do, as we kind of normally understand induction, do it multiple times. We're talking about a thing that happened once. It may not ever happen again in the same way. So on that basis, kind of we need a different form of argument or reasoning. And hopefully we can link it up with other kinds of intuitions or other kinds of inferences that are inductive or even deductive. But it's never going to become that. It's Napoleon is one guy. Right? That's kind of what he is. It may be that at this time of his career, events were being recorded in some way not now dreamed of. That some ingenious creature on a neighboring planet was photographing the Earth. And that these pictures on a sufficiently large scale may sometime come into our possession. He was like, they're out there. The UFOs that were looking at Napoleon, thank God. Or that some mirror upon a distant star will, when the light reaches it, reflect the whole story back to Earth. So never mind how improbable these suppositions are. Everything which happens is infinitely improbable. I love that line. Everything which happens is infinitely improbable. It's like really nothing should happen. So the fact that things happen at all is infinitely improbable. The fact that any particular thing happens is infinitely improbable. Which is also something that admits of strict demonstration within statistics. That there's an infinitesimal possibility of a dart hitting any point on a dartboard. It's impossible. Well, of course it does hit a particular point. But it's infinitesimally possible that you would pick a particular point that it would hit ahead of time. It might be one way to interpret that. The hypothesis asserts that such facts, when they do occur, will be of a nature to confirm, and not to refute, the existence of the man. We have, in the impossibility of inductively inferring hypothetical conclusions, a second reason for distinguishing between the two kinds of inference. A third merit of the distinction is that it is associated with an important psychological, or rather physiological, difference in the mode of apprehending facts. And this is the part of the paper that, even though it comes at the very end, I think is very, very fascinating and interesting to think about. Induction infers a rule. Now, the belief of a rule is a habit. That a habit is a rule active in us is evident. This is also where a person becomes annoying. It's like he'll just say that things are obvious that to almost any other human being are not obvious, but he's like, that a habit is a rule active in us is evident. Okay. That every belief is of the nature of a habit, insofar as it is of a general character, has been shown in the earlier papers, which we didn't read. Induction, therefore, is the logical formula which expresses the physiological process of habit formation. Hypothesis substitutes, for a complicated tangle of predicates attached to one subject, a single conception. We have all sorts of different kinds of things going on, and we're like, but that is one thing. Now, there is a particular sensation belonging to the act of thinking that each of these predicates inheres in the subject. A peculiar sensation, I should say. In hypothetic inference, this complicated feeling so produced is replaced by a single feeling of greater intensity, that belonging to the act of thinking, the hypothetic conclusion. Aha! It's that aha moment. When it like all comes together, Sometimes we even say it's coming together. I see it, I get it. Now, when our nervous system is excited in a complicated way, there being a relation between the elements of the excitation, the result is a single harmonious disturbance. It's a nice oxymoron. Harmonious disturbance, which I call an emotion. Thus, the various sounds made by the instruments of an orchestra strike upon the ear, and the result is a peculiar musical emotion, quite distinct from the sounds themselves. So here he means emotion in this kind of very broad and somewhat weird way, which is that all of these various kinds of sensory intuitions that I have, when I bring them together and I make an experience out of them, the experience, the kind of emotional experience, doesn't always have to be what we normally mean by emotion. It's even broader than that. It would include that, but it's even broader than that. The fact that I'm able to say that anything is like a thing is a hypothesis. This emotion is essentially the same thing as a hypothetic inference, and every hypothetic inference involves the formation of such an emotion. This is the part that I'm just like, this bowled me over when I first read it. Emotion is essentially the same thing as a hypothetic inference. 1. And every hypothetic inference involves the formation of such an emotion. 2. Boom. And it's like, why did I have to go all through all this stuff about Barbara and Barocco to get here? Well, I don't know. That's just how Peirce is, but maybe it's important, actually. We say that, therefore, that hypothesis produces the sensuous element of thought, and induction the habitual element of thought. As for deduction, which adds nothing to the premises, but only out of the various facts represented to the premises, selects one and brings the attention down to it. This may be considered as the logical formula for paying attention, which is the volitional element of thought, and corresponds to nervous discharge in the sphere of physiology. It's a super weird, it's like one of the weirdest paragraphs ever written, but I love it. Very, very weird. So it's like habits, emotions, and attention are all the various kinds of forms of inference that classical logic might study. There you go. Another merit of the distinction between induction and hypothesis is that it leads to a very natural classification of the sciences and of the minds which prosecute them. What must separate different kinds of specific scientific men, more than anything else, are the differences of their techniques. We cannot expect men who work with books chiefly, have much in common with men whose lives are passed in laboratories. Fair enough. But after differences of this kind, the next most important are differences in the modes of reasoning. Of the natural sciences, we have, first, the classificatory sciences, which are purely inductive, systematic botany and zoology, mineralogy, and chemistry. Then we have the sciences of theory, as above explained, astronomy, pure physics, etc. So this is like, more deductive. Then we have the sciences of hypothesis, geology, biology, etc. Now, one of the things that's interesting is like people no longer seem to really care at all. Not much, but almost not at all about the kind of classification of the sciences as being kind of neat and separate categories. And I think that there's probably a much more complicated history and story as to why that is. But it used to absolutely obsess people that the image of knowledge would be a kind of composite. Like you could add up all of the sciences and you'd have an image of at least actual knowledge. Maybe not all possible knowledge, but actual knowledge. And I think Peirce wrote a number of pieces that were in that line. He even created his own like giant classification of the different sciences and how they map them out. But no one would do this in a kind of serious way today. I don't think. I mean, maybe I'm wrong and people know about this kind of project that's happening somewhere in scientific thinking. But to me, it seems like most people are more interested in grant writing and being like, sure, we're interdisciplinary. Like, I'm doing biology and chemistry, but it's called biochemistry. Like, who cares about what kind of inferences I'm using to do it? Like, so in some sense, our kind of thinking about science is not something that happens within science as much anymore in contemporary scientific research. That's a bold claim, but that is my sense of it. I might be wrong. But it seems like the thinking about science and its kind of various divisions is maybe something that philosophers of science do, but scientists themselves, I think, are mostly insouciant towards that kind of stuff today. But Peirce was a scientist. He was also a philosopher, but he was a scientist. There are many other advantages of the distinction in question, which I shall leave the reader to find out by experience. If he will only take the custom of considering whether a given inference belongs to one or other of the two forms of synthetic inference given on page 472, I can promise him that he will find his advantage in it in various ways. So, when are we doing deduction? Very rarely. When you're doing Sudoku, maybe in the morning or in the evening. When you're doing some math problem, maybe. maybe you're doing deductive inference. Very, very rarely. When you're in an argument class doing a kind of exercise, maybe you're doing deductive inference. Most of the time, the kind of inferences we're doing are synthetic. And Peirce is trying to ask you to say, is it useful to make this distinction between induction and hypothesis? Am I inferring a rule about things from lots of different cases? Or am I inferring the case itself? And a different kind of logical force, but also a different kind of logic applies to that. And they can be converted into one another in some cases. They can be used to support one another, but they're different. Well, anyway, that was my weird stream about logic for today that got interrupted. Apologize for that, but hopefully you enjoyed this stream, and I'll come back next time for the next thing, which I'll read, which will probably be very, very different from what we looked at today. I imagine. All right. See you next time.